Hello and welcome to chemistry. This is chapter or unit 10, thermochemistry. It says here chapter 17 from your textbooks. And our essential question for this unit is how is the energy change of a process measured? So we'll dive right in uh, first by looking at some kind of daily sub-questions. So how is the energy change of a temperature change in a substance measured? And then how is the energy change of a phase change measured? So you can see that those are two different processes, a temperature change and a phase change, uh, and there's going to be different ways that we can go about measuring energy in both of those processes. A little background information then first on phase change calculations. When we add energy, it can do one of two things. It can speed up particles, which is a change in temperature, or it can spread out particles, which is a phase change. And so there's two different calculations. If we have a temperature change or speeding up particles, we're going to use this equation here, and it's E equals mc delta T. Sometimes people drop off that little subscript P, but C subscript P is just one variable, and it means the specific heat constant. The M stands for mass, and the delta T stands for change in temperature. E also stands for energy. And this is a good time to just mention that you should be taking some notes in your student notebooks here while going through and listening to this video. So you'll want to record this stuff into your notebooks. The second type of calculation then is when we're spreading particles out or changing phase of matter. So here, our equation is a little bit different. It's E equals moles times either HF or HV. HF is the molar heat of fusion, which we'll deal with whenever we're melting or freezing a substance. And then HV is the molar heat of vaporization, which we'll deal with whenever we are boiling or condensing a substance. So the next thing that we'll look at here is a diagram, and you've seen this before, a phase diagram. And so we want to know what's happening to the particles at each step and what states of matter are present. So the first thing I want to pull up are just these three letters here: solid, liquid, and gas. I want to make sure that we're aware that it's at the diagonal points here that we have a substance heating up, so it's going to stay liquid this whole time. It's just getting warmer and warmer. These flat lines then, if we drew out the variable here, we would see that the y-axis is actually going to be temperature here, as the x-axis is energy. So as I'm adding energy, I'm not changing the temperature in these flat portions. This is where our phase changes are occurring. Now, as far as energy calculations go, we want to know when to use each different method. First method I said was the E equals mc delta T equation. And so we'll use this when we have a solid, a liquid, or a gas, and we're changing its temperature. We can't use this for the flat lines. There we use either E equals moles times HF or E equals moles times HV, the heat of fusion here and the heat of vaporization up there at the top. I want to point out one more thing before we move on from the diagram here. You'll notice that the line for the freezing and melting is a little bit shorter than the line for boiling and condensing. This is because it takes more energy to turn a substance into a gas, really separating those particles out to gas phase, than it does to just kind of pull them apart a little bit going from solid to liquid. So something worth pointing out there. So we've got some example problems of how we'll calculate energy change in these processes. The first question asks how much energy in kilojoules is needed to evaporate 24.8 grams of water. I'm honing in on the word evaporate here. This tells me we've got a phase change going on, and it tells me that we're going to use E equals moles times the heat of vaporization, because this is the boiling or condensing vaporization process. Now, we don't have the variable for moles or the variable for the heat of vaporization, but we can get both. The first thing we're going to do is we're going to take our 24.8 grams and we're going to convert that to moles by dividing by 18.02 grams for every 1 mole. Grams will cancel out when we do that, and now we have a substance of moles. Now, you can use the equation, but a lot of times these problems work better just simply as a as a conversion problem. So in this problem here, we're going to multiply by 40.7 kilojoules for every 1 mole. Now you might be wondering where I got this 40.7 kilojoules. And moving forward, I want to make sure that you take a look at, there's a chart on Schoology that provides all of the data that we need here. So there's going to be a few different tables on the document that you download from Schoology, and one of the tables is going to have the HF or HV values. I believe that the document is labeled as constants tables, but it should be in the Unit 10 folder. So you probably want to open that up to answer some of the questions in the video here. So I'll let you do the calculation, and then we'll see what we get as an answer. So hopefully you were able to do this calculation here. You should have 56.0 kilojoules at this point. Grams canceled out, moles canceled out in the second step, and then we have the 24.8 divided by 18.02. That number's a little bigger than 1, and then we multiply by 40, so it really makes a lot of sense that we'd get an answer, right around 56 here. And that's 3 significant figures dictated by both the gram value and the kilojoules value that we had here. And of course, we said we got this from the chart there for the heat of vaporization. Our second example now asks how much energy is needed to raise the temperature of 28.6 grams of water from 45.0 degrees Celsius to 68.0 degrees Celsius. So we're raising the temperature. That tells me right away this isn't a phase change part here. This is an E equals mc delta T type of problem. Now we got to identify some variables. We're asked to calculate energy, so we should be able to find the mass, which is 28.6 grams. The value for C, we have to go back to our heat constants table and get the specific heat of water. And that's 4.18, for calories, it's 1.00 calories per gram degree Celsius. Now how much is needed to raise the temperature from 45.0 to 68.0? So delta T is just 68 minus 45, and that's 23 degrees Celsius. So we got all of those values there. Now we just plug them into the equation. E equals m times C times delta T. You should notice here that the unit of grams is going to cancel out with the grams in the denominator of the C unit. And then the degrees Celsius also is going to cancel. And so we're going to be left with the unit of calories once we do this math. I'll ask you to do the math and get the right answer with the right number of significant figures. And then here it is, 657.8 calories, but we have to round that to 658 calories because we're only allowed 3 significant figures in this problem. So those problems, I hope that you feel like weren't too difficult because they're going to get harder for us. The next example here asks us how many grams of ice at 0 degrees Celsius could be melted by the addition of 2.25 kilojoules of heat. So I gave you kind of a little bit here already, but the equation is going to be E equals moles times HF because we're talking about melting here. So when we see that melting, I know we're going to need the HF. But this time, we don't have grams, but we're given energy. So we're going to start with what we've been given there, the 2.25 kilojoules of heat. And in order to do this problem, we need to divide by the number of kilojoules in 1 mole of this substance here. And so when we look up the HF value, we get 6.01 kilojoules. That allows us to cancel out kilojoules and get to a unit of moles. Then we go from moles to grams using the molar mass of water, 18.02 grams per mole. Now we see, we already had kilojoules cancel out, we already had moles cancel out, and so we now have 6.75 grams as our answer here. So we just kind of worked backwards from what we had done in problem number 1. All right, so problems are still getting a little tougher here. How much heat is required to change 50.0 grams of ice at negative 10.0 degrees Celsius to water at 50.0 degrees Celsius? So the interesting thing about this problem is there's actually a few different steps that we need to consider. The first thing that has to happen is the ice has to heat up. And when we have a substance changing temperature, we're going to use E equals mc delta T. Then the ice has to melt. So here we use E equals moles times the heat of fusion. And then the liquid water has to heat up, which means that we use E equals mc delta T again. And you might be thinking you can combine a couple of these steps, and you can't. So we're going to kind of jump right into the calculations here. In step 1, E is equal to 50 grams times 2.10 joules per gram degree Celsius times 10 degrees Celsius. The 50 grams, I hope you can see where we got that from. That was given to us in the problem. Now, you got to remember here that we have ice because we're down below 0 degrees Celsius. So if you look at the chart of specific heat values, the specific heat for ice is different from the specific heat of water. It's 2.10 joules per gram degree Celsius as compared to 4.18. Water, liquid water, is very well known as having a high specific heat, meaning it takes a lot of energy to change its temperature. Ice doesn't quite have as high of a specific heat. And then you also might wonder where we got the 10 degrees Celsius. That comes from a little tricky calculation. Whenever we're trying to get delta T, you have to subtract one temperature from another. So you might jump into taking 50 minus negative 10 and getting 60 degrees Celsius, but we're just going from negative 10 up to 0. And 0 minus negative 10 is 10. So we take 50 times 2.10 times 10, we get 1,050 joules. And again, you see grams cancel out, degrees Celsius cancel out, so it makes a lot of sense that our answer would be in joules here. That's just 1/3 of the problem. Now we go to step 2. We're given the 50 grams of ice. This time we got to convert from grams to moles, so we divide by 18.02 grams per mole, the molar mass of water. Probably you're kind of memorizing that number at this point. We're going to be using it a lot, this unit. And then we're going to multiply by the heat of fusion, which is 6.01 kilojoules per mole. So now we have grams canceled out. Now we have moles canceling out. We're left with a unit of kilojoules. And when you multiply all these numbers together here, you get 16.7 kilojoules. That takes us into step 3 then. Here we have 50 grams times 4.18 joules per gram degree Celsius times 50 degrees Celsius. So in this case, we now have water. The ice has melted. It's the same 50 grams, but we're going to multiply by 4.18 joules per gram degree Celsius. It takes more energy to increase the temperature of water by a degree. And then we're going from 0 to 50, so 50 degrees Celsius here. And that gives us 10,450 joules. And just kind of looking at this quickly, we've only got 3 significant figures, so it should actually be 10,500 joules. I kind of left it where it was because the next step is we have to just add these energy values up. But you've got to be very careful. We don't have the same units over here. When we do equals mc delta T, we get joules, or we could get calories, but that's inconvenient because when we do the phase change steps, we're always going to get kilojoules. So we want to get joules for steps 1 and 3, kilojoules in step 2. We've got to get those units on the same page. My recommendation is to put everything into kilojoules for these types of problems. The reason is because of significant figures, actually. Students tend to have a lot easier time getting the right number of significant figures when you're dealing with decimals. When we have numbers that are bigger than that, where there's no decimal and this 0 has to be rounded, that's where we kind of start running into some trouble with significant figures. So let's make it easy for ourselves. Let's solve it in kilojoules. I divide 1050 by 1,000. I divide 10,500 by 1,000, which I didn't show here, but I have now 1.050 kilojoules, 16.7 kilojoules, and I should have here 10.5 kilojoules. And I'm just going to double check my significant figures here to make sure I have the right answer here. So now I'm actually getting 28.25 kilojoules, which would round up to 28.3 kilojoules. So, I wouldn't take points off on the test for you having, 28.2 kilojoules here, but the answer, if you're getting it on your calculator as 28.3 kilojoules, I think that's the best answer in this problem because of significant figures. So this problem had 3 steps. We had heating up ice, melting ice, heating up some water. I can give you a problem that has as many as 5 steps in it because we could heat this water all the way up till it boils, and then we could heat that gas up after that. So you could have as many as 5 steps. However, sometimes it's the 3 or 4 step problems that are the hardest because if it's 5 steps, you start with ice and you go up to the gas phase. When it's 3 steps, you got to kind of figure out where you start and where you finish. So tricky problem here. You want to be prepared for stuff like that on your homework assignments and on the test. And the other thing I'll mention is that if you had 28,300 joules, that would be perfectly fine. But here, this is what I'm talking about where people struggle with significant figures. If you have 28,250, sometimes students struggle when they have to round a whole number like that and get rid of that 50 and round it up to 28,300. Whereas typically it makes a lot of sense for people to round, when it goes from 28.25 to 28.3. So that's why I would try to move to kilojoules in these problems. So that covers the first concept here with the phase changes as well as with the temperature changes of a substance. So we've answered how energy can be measured in 2 different processes. Of course, that was our unit essential question. How is the energy change of a process measured? And now we've got a sub-question, and it's a new sub-question. How can energy be used to determine an unknown substance? So this is, I think, a really cool and powerful concept. We're going to do a lab with this as well. So our objectives here are we're going to calculate the energy released or absorbed when an object is heated or cooled. And then we're going to perform a calorimetry experiment to determine the specific heat of a substance. I'll explain what calorimetry is in just a minute. And then we're also going to determine the error of a device and the error of a measurement in lab. So I put that as a third objective. We'll be calculating percent error with this stuff. We won't be using the most high-tech of equipment, so it's a worthwhile endeavor to measure the error there as well. But the first 2 goals here are really what we're going to focus on in the problems here in the notes. So when we measure a heat change, that's called calorimetry, and it's a precise measurement of heat change during a process. Here's the central concept, the law of conservation of energy. It says that the heat released by a system has to equal the heat absorbed by the surroundings. And what that means is the law of conservation energy. Energy is conserved. Now, we know in real life, if we have a reaction, we probably won't be able to perfectly insulate it and trap all the heat. Some of that heat's going to get lost, and we won't be able to measure it. But we're going to assume, if we have good equipment, that we can capture all that heat that comes from a reaction, and we can measure how it's being absorbed by surroundings. And then we can set those 2 values equal to each other. So a calorimeter is an insulated device used to trap heat during a reaction. In our class, this is going to pretty much be like a styrofoam cup with a little plastic coating on the inside and outside, and it's going to hopefully trap as much heat as possible in the reaction. It has a little cover so that we don't lose heat up above as well. So we try to insulate a reaction or our process as best as we possibly can. When you go on to college and you're taking probably a physical chemistry class where they measure this type of stuff a lot, you'll use a fairly expensive, they call it a bomb calorimeter. I don't exactly know why. I guess it kind of looks like a bomb, and it's a strong device. It's thickly insulated with really good materials, and it does a much better job of very precisely capturing all of the heat from a reaction. We don't have that kind of money here. So we'll just be using a lesser technologically advanced device, but I think we'll be able to get pretty good results and understand the concept from it. Now, I want to talk about enthalpy, which is used as an H here, and that means the heat content of a substance. So the heat content of a substance can change as it heats up or cools down. It can either gain heat or lose heat. So we measure it as delta H, a change in enthalpy. Q and delta H are basically the same measure. Again, as you go on to maybe AP chemistry or especially physical chemistry in college, for those of you who take it, you'll start to differentiate between some of these terms, Q and delta H. It's a little more complicated than we're presenting it right now, but for right now, let's just use those variables interchangeably. If you have an endothermic reaction, you're going to have a positive delta H value, which means the substance gains heat. And if you have an exothermic process, the substance loses heat, so we say that it has a negative delta H value. Typically, we like exothermic reactions a lot because they provide the surroundings with energy. For instance, they heat our homes, they heat our cars, they run our power plants. We like exothermic processes a lot. We do use endothermic processes in things like batteries, where we need to kind of store energy for later use. So that's a little bit of an application of those concepts. We're not going to worry too much about the positives and negatives as we go through these calculations. Again, if you take some physics classes later on, I've had classes where when they have a multiple choice question, all the numbers that they have, with a positive answer, they also have with a negative answer, and you really have to understand that endothermic, exothermic concept. You'll get a couple questions like that in the multiple choice section where it's kind of identifying exothermic, endothermic, but I'm not going to penalize you for having a negative or positive answer, as long as you're showing the right work. So my answers in here are all going to be positive because we're talking about some phase changes and stuff. So we start out with the law of conservation of energy here, that the energy absorbed by a substance has to equal the energy released. And in this problem, it says, what would the final temperature be if 25 grams of ice at 0 degrees Celsius is placed in 100 milliliters of water at 35 degrees Celsius? So what I'm saying here is we've got ice in water. The ice is obviously going to heat up, which means it's going to absorb some energy. And then the water is probably going to cool down as the ice melts into it. And I'm already kind of foreshadowing a couple things that have to happen. We know the ice starts at 0 degrees Celsius, meaning the ice doesn't actually have to heat up at all. It's going to melt. The ice is going to melt. And then when it melts, it'll be water at 0 degrees Celsius. As the ice melts, that's going to cool this water at 35 degrees Celsius down a little bit. And then probably it won't cool it down all the way, so we're going to have some warm water mixed with some cold water, and then that will continue to pump energy out of the water that's warm and into the cold water, and we'll get to a temperature that's somewhere in the middle. Now, I can tell you this problem is going to be pretty tricky, and it's going to be more difficult because we're looking for that final temperature value. On some of your assignments at home, this problem will be a little easier because you're not going to be solving for the final temperature, which you'll see makes this problem a little more difficult. So this is what you can break our equation into. When I say energy absorbed, we're talking about the ice. It's first going to melt, which is moles times the heat of fusion, and then it's going to increase its temperature as mc delta T. Now, I've labeled this as ice, but we have to remember the ice has already melted, so that's going to affect this stage of the calculation a little bit. Over here, we have the mc delta T of the water, and so again, this will really be the cold water, and this will be warm water, but I just labeled it as ice to differentiate it there. So this is probably the trickiest part. If you can master this step, you're in good shape for these kinds of problems. What I want you to see is the energy absorbing. What's happening to the ice? How is it absorbing that energy? Well, first, we have a phase change, so we have a phase change step. Then it's going to warm up, so we have a change in temperature step. Now, we don't anticipate that this water is going to get down to the freezing point. So we're kind of making an educated guess there, but that makes a lot of sense because there's more water, and it's quite a ways from the freezing point, whereas the ice is already right there. So we expect the ice to melt. We don't expect the water to freeze. So all the water has to do is cool down, according to MC delta T. You can actually keep this problem set the whole way through as one side equals the other side, but that gets a little tricky. It's a good math exercise, but what I'm going to do is I'm actually going to break it apart a little bit. Before I break it apart, though, I want you to see that we're going to replace delta T here. So it's the same thing. But for the ice, it's going to have a temperature final that's going to be higher than its initial temperature. The ice is initially at 0 degrees, but it's going to heat up. So delta T should be equal to the temperature final minus the temperature initial. On the other hand, the water is going to be equal to the temperature initial minus the temperature final. It's initially at 35 degrees, and it's going to cool down so that the final temperature should be lower. So we'll get positive numbers in both of those places. And now we're off to the steps. So I just broke this up as I said, and the first step here is the moles times HF. We're going to take 25 grams, that's the grams of ice. We're going to multiply by 1 mole over 18.02 grams, so now we have moles of ice or of water. And then we're going to multiply by 6.01 kilojoules per mole. That's the heat of fusion, which we get from the chart there. And again, that's that constants tables chart. You want to make sure you're checking, looking at that, making sure it makes sense why we got the number here that we are getting. Because there's a bunch of different numbers on those tables, and there's 3 or 4 tables on that worksheet. So you want to know how to pick out these numbers. You'll be given those charts on the exam. I should let you know that right away. You don't have to memorize any of that stuff, but you do have to understand how to use the numbers, what number you're looking for. Heat of fusion is the 6.01 kilojoules per mole. So let's calculate that with the appropriate significant figures and the unit. And then I have 8.34 kilojoules here as my answer. So that's step 1 here, and we have the unit of kilojoules, which makes a lot of sense for us. Just checking our math, it makes sense that we'd get a number bigger than 6 because 25 is bigger than 18, but not too much bigger, so this is great. Now we're on to the second step, and again, that is the change in temperature of what is now water. So here we use E equals mc delta T. We know the mass is 25.0 grams. Now the specific heat, I've been hinting at this for a while, it's the specific heat of water, not of ice, because the ice already melted. So it takes a lot more energy to heat up that water now. And then we're multiplying by, and this is where it gets really complicated, we have to keep that TF in there because we don't know what TF, that's what we're looking for. We do know the initial temperature of the ice. The initial temperature is 0 degrees Celsius, and that works out really, 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 really well for us. If we were using any substance besides water that didn't have a temperature of 0, we would have to do a calculation. It would make the calculation much more challenging. But because we know this is 0, that's great. And when we do the math, you should actually get 104.5 TF. I took 25 times 4.18 times TF. That's the variable I have here. And then I'm just multiplying by a 0 as I distribute these to the 0. So that's going to totally drop out of this term. And all I've got to worry about now is the 104.5 TF on this side. All right, so we go to the other side of the equation where we have the water. It's 100 grams times 4.18 joules per gram degree Celsius times 35.0. And then we also have to take the 100 times 4.18 and distribute that to the TF value. So now I have 14,630 joules minus 418 TF. So I know this is complicated. First thing we did was we took the moles times the heat of fusion to figure out how much energy is going to be absorbed by the ice as it melts. Then we wanted to figure out how much energy is going to be absorbed by the now water, the cold water, as it heats up. And we don't exactly know, but we know it's going to be 104.5 times TF. And then we want to know how much energy is released by the water as it cools down. And again, we don't exactly know, but we have 14,630 joules minus 418. Again, you could do this all together, but I think it's easier to kind of split everything up. But now we need to recombine things. So here's what we have. 8,340. I got rid of the units right here, but I'm gonna bring them back and show them to you in a second. But it looks really scary when the units are in there. 8,340 joules plus 104.5 times TF equals 14,630 minus 418 TF. I converted the kilojoules to joules because we have this joule value here, and as it turns out, there's going to be a lot more joule values that are around. So we wanted to convert kilojoules to joules in this type of problem, and that's going to pretty much be the case all the time for this type of problem. Remember before I had said you can keep it in kilojoules, it would be easier. Here we've got to go to joules. Now I pulled back all the units here. So we know 8,240 is a unit of joules. The 104.5 TF, if you look at the units, and that's going to be up in this step right here, we took grams times joules per gram degree Celsius. So the grams canceled out, and we now have joules over degrees Celsius times TF. So it's 104.5 TF. That's the variable we're looking for. So it would have been really confusing to have joules over Celsius, times TF. I got rid of those, and you don't have to show these in the problem, but I want you to understand when we get to the end why the unit is what it is. On the other side then, 14,630 joules minus 418 TF. Again, that was 100 grams times 4.18 joules per gram degree Celsius. So the grams canceled out, and we were left with joules per degree Celsius. And again, that was 418 TF. So when you're doing the problem, I would just use this top version. I probably wouldn't write out all the units in here because it's going to get really messy, but I want you to understand when you get to the end how you determine what the unit is. So we've got to what we call rearrange the equation or combine like terms is what your math teachers would probably say. We're going to subtract the 8,340 joules on both sides, which means 14,630 minus 8,340 joules. And then on the other side, or the other part of this is we're going to add 418 TF to both sides. So we're combining our TFs and we're combining our joules here. And so now I have 522.5 TF equals 6,290 joules. Now it's easy. We're just dividing by the 522.5 on both sides. And when I do that, we've got to remember the units again. This was 522.5 joules per degree Celsius times TF. So it's confusing if it's over here, but I need to kind of bring it back. And when we get our final answer, when you do this calculation, you get 12.0 degrees Celsius. The 12.0, that's just 6,290 divided by 522.5. But how do we get degrees Celsius? Well, we have joules divided by degrees Celsius. You can remember that because you're multiplying by the reciprocal there. So instead of thinking of it as joules over joules degrees Celsius, think of it as joules times degrees Celsius per joule. Those joules cancel out. Or you can remember my favorite rap song, started from the bottom of the bottom, now we here. The degrees Celsius was in the bottom of the denominator, and so unless stuff gets canceled out along the way, degrees Celsius makes it up to the top here as our unit. So 12.0 degrees Celsius, really challenging problem here. Remember, I won't often have you solve for TF. That's a really difficult question for me to ask for you to get TF here. What I will ask you to do is a similar problem like this, but you'll probably be solving for like the mass, which makes it easier because you don't have to break this up and then distribute, and it adds a lot of extra steps. So thanks a lot for working with me. I think it's great that you can do a problem like this, and you'll see something similar. You might see one like this on the homework, but on the test it'll be a slight bit easier. Not that much easier though. All right, now we're going to have some fun here. We're going to do a practice problem that's not in your notes packet, but you might want to kind of draw it in on the side, and maybe by the time you're watching this video, I'll have added it into the notes. This is kind of a fun problem. So in an attempt to defend yourself against a vampire, you must determine the identity of a silver bullet that has been mixed in with iron ones. I'm not sure if bullets are made of iron. Probably they're not, but that's our other ones here. And so calorimetry will allow us to do this, to determine what the bullet's made of. You add, so what you did is you added an 11.9 gram bullet. So you'd weigh the bullet, and that's heated to 100 degrees Celsius in boiling water. This is what we're going to do in the lab. We're going to take a metal and we're going to put it in boiling water, which we know is going to get it up to 100 degrees Celsius as energy flows, out of that hot water into the bullet. So once it's good and warm, we're going to take the bullet out of the water and we're going to place it into 54.0 grams of 20.0 degrees Celsius water. Now the final temperature is recorded to be 21.0 degrees Celsius. And that's what you'll be doing in lab, is kind of getting that final temperature. So my question here is, what is the bullet made of? Iron or silver? So we start out with the law of conservation of energy. The energy being absorbed by the bullet has to equal the energy. The energy being absorbed by the water in the calorimeter has to equal the energy being released by the bullet. So the bullet absorbed energy while it was boiling, but now it's releasing energy and it's being absorbed by the water in our calorimeter, and that's really important that we know all this information about that water. So we can break this equation down a little further. Well, we've got some heat changes here. So the mass of the metal times the specific heat of the metal times the change in temperature of the metal should be equal to the mass of the water times the specific heat of the water times the change in temperature of the water. Now, we don't know what the specific heat of the metal is. Once we figure out the specific heat of the metal, we'll be able to look on one of the charts we have, and we'll be able to see whether or not we have a silver or iron bullet. But in the meantime, we've got to calculate the specific heat of the metal. So I'm going to divide both sides by the mass of the metal and the change in temperature of the metal. So you see that here. We cancel out some variables. On the other side now, we've got kind of a large equation there, a lot of different variables. Let's move things around. So the specific heat of the metal equals mc delta T of the water divided by m delta T of the metal. Now we're just plugging some numbers in. It's a little bit tricky here, though. So the mass of the water is 54 grams. We know that. The specific heat of the water, we have to go to our chart of specific heats in the constants tables. And we'll get that value in joules for this problem, though you could do it in calories and get the same answer. We'll also then get the delta T of the water. Now that's going to be that's going to be the final temperature of the water. So the water heated up to 21.0 degrees Celsius from 20.0 degrees Celsius. So you're going to take 21 minus 20 there, and so we get 1 degree Celsius for the change in temperature of the water. On the bottom then, the mass of the metal, that's 11.9 grams. And then the change in temperature of the metal started at 100 degrees Celsius. And then it cooled down as it released energy down to 21 degrees Celsius. So 100 minus 21, and I believe that gives us 79 degrees Celsius. So we plug everything in here. We do the math. I'll let you guys do the math and also get the correct unit for this problem. And then here it is, 0.24 joules per gram degree Celsius. So we would check our chart and we would find that that is indeed a silver bullet. So I took the 54 grams, that canceled out with the grams here. The degrees Celsius canceled out, so we're going to just keep that unit for the specific heat, which is joules per gram degree Celsius. If we had this value in calories, the number wouldn't be the same, but it would be the number for the specific heat of silver in calories. So we do indeed have a silver bullet. You're ready to defend yourself against that vampire here, and you're also ready to go on to do the homework assignments here. So there's a couple activities that you'll see on Schoology here that you can complete. And then, of course, you will do the lab as well, and then we'll also have a test on this concept here. This is just the first video of the thermochemistry unit. There'll be another one here at least. So that is it for today's lesson.